Hello guys, you're welcome to this lesson. In this lesson, I'm going to discuss how electron affinity varies on a periodic table. So we've learned that when we say electron affinity, that is the energy that is being released or that is being absorbed when 1 mole of an electron is added onto an isolated gaseous species to form a singly charged anion. Is that okay? Or when 1 mole of an electron is added onto the outermost shell of an isolated gaseous species to form a singly charged anion. Is that okay? Now, how does this EA varies on the periodic table? So in our first periodic variation, I'm going to look at how it varies across the period. So electron affinity variation across the period. Electron affinity increases. So the variation is that it increases across the period from the left to the right on the periodic table. It means that once you're moving from the left-hand side to the right-hand side on the periodic table, the affinity or the love for electron gradually increases. And what is the reason? So in our previous lesson, we learned that a factor that we can use to talk about the variation across the period or down the group can be one, atomic radius. But to make it more simplified, we are going to use a simple idea here. EA, or electron affinity, increases with increasing effective nuclear charge. Or attraction. So, in the generalization, electron affinity increases with an increase in effective nuclear charge or effective nuclear attraction. What is the meaning of this? It means that we know that once we're moving across the period, we've learned previously that moving across the period, there is an increase in number of protons, and an increase in number of protons indicates what? An increase in nuclear attraction. Why will nuclear attraction increase? Once you're moving across the period, the number of shells is kept constant. So the inner shell, which contains the inner shell electrons, is also kept constant. Meaning that electrons that can shield or that can cause electron repulsion to bring about a reduction in attraction made by the proton for the valence electron is reduced. Is that okay? So once you're moving across the period, there is an increase in nuclear attraction. And once nuclear attraction increases, it increases effective nuclear attraction. Is that okay? Now the question is, how will this influence electron affinity? Electron affinity means loving for an electron. Electron loving. So if an atom has a high electron affinity, it means that it has high feelings for electron. It wants an electron to be added onto its outermost shell. Is that okay? And since across the period there is a high attraction for electrons, the moment I want to add an electron, it becomes easy. Why? Because the moment you add the electron, since there is a high nuclear attraction across the period, the added electron is easily accommodated in the shell. Let's take a simple diagram as a scenario. So I have here my protons in the nucleus. Is that okay? Then I have my inner shell electrons, and then I have my valence electron. If the proton attraction here across the period, we are saying that it's increasing. It means that the attraction for this electron and this electron is very high. And also the attraction for this electron is also very high. And this one is explained as effective nuclear attraction. So effective nuclear attraction is being increased across the period here. So if I want to add an additional electron, that is, I have high affinity for an electron, once I add this electron, since there's a high attraction taking place here, it means that this added electron can be accommodated in this atom's shell. Are we getting the point here? So electron affinity increases once there is an increase in nuclear attraction, because the nuclear attraction will enable the added electron to be accommodated in that atom's shell. Is that okay? So that is the reason why we say EA increases with increasing nuclear attraction. Mathematically, we can say that EA is directly proportional to effective nuclear attraction. Let me put it this way, ZFF. EA is directly proportional to effective nuclear attraction, because the work of effective nuclear attraction is to attract the valence electron. Is that okay? And that attraction is very high once you're moving across the period. You get the point? So since that attraction is very high, and I have affinity for more electrons, and I want to add another electron, once I add that electron, in order for that electron to be accommodated, I need a certain strong attraction that will help me to accommodate that electron. And that strong attraction is the effective nuclear attraction. And it is very high once you're moving from the left to the right across the period. And since it is very high, and it will help me accommodate my added electron, my affinity for electron will also increase the moment I am moving across the period, because there will be some attraction to help with the accommodation of the added electron. That is the reason why one of the factors that helps to explain the variation across the period is the atomic radius. Why the atomic radius? Atomic radius decreases across the period due to an increase in effective nuclear attraction or effective nuclear charge. So across the period, attraction for the electrons and the valence electrons is very high. So the distance between the proton and then the valence electron becomes very, very small. So the moment you add an additional electron, it becomes very easy for the proton attraction to accommodate that added electron in the atom shell, or the shell in which the electron is being added. Is that okay? So electron affinity gradually increases across the period from the left-hand side to the right-hand side. So considering the period 2 element, for example, we expect nitrogen to have a higher electron affinity than carbon, and carbon also have a higher electron affinity than boron, and boron also than beryllium, and beryllium also than lithium. Is that okay? Please, you get a point here. Again, in the initial explanation for electron affinity, we said EA can be the energy that is released. If energy is released in the process, it means that it is an exothermic process. If energy is being absorbed for EA, it means EA is endothermic. For exothermic process, the EA will have a negative value. For exothermic, the EA will have a negative value. For endothermic, the EA will have a positive value. Is that okay? So once we look here, I have the electronic configuration for lithium, beryllium, boron, carbon, and the nitrogen. They are all in period 2 with their corresponding EA values. Lithium has EA of negative 60. That is exothermic. I will explain that as well. Beryllium has EA of positive 66. That is endothermic. That is energy is absorbed. Here energy is released. Boron, EA of negative 27. It means energy is released. For carbon, EA of negative 122. Energy is released, exo. Nitrogen, EA of negative 31. That means energy is also released. Why the negative EA value and why the positive EA value? In the simplest form, if the addition of an electron will be accommodated with a vacant orbital, if there is a space in that orbital, energy will be released. Is that okay? It means that the electron repulsion over there will be very low, such that energy will be released in the process. But if the addition of an electron is to an already fully filled orbital, there's going to be an increase in electron repulsion. And while there's an increase in electron repulsion, energy will be needed to accommodate that incoming electron. And if energy will be needed, it means energy will be absorbed. And the moment energy is absorbed, the EA becomes indeterminate, or it becomes positive. Is that okay? That is the reason why we have the negative EA values and then the positive EA values. Is that okay? So electron affinity is the enthalpy change or the energy that is released or absorbed when an electron is added onto the atomose shell or is added onto an isolated gaseous atom. Is that okay? And we are saying that this energy will increase the moment there is an increase in nuclear attraction, which gradually increases the effective nuclear attraction, because the additional electron that is being added needs to be accommodated in whatever shell it will find itself in. Is that okay? And since across the period there is an increase in nuclear attraction, which gradually increases the effective nuclear attraction, once the added electron is being added, it is easily attracted, so it will be accommodated in that atomose shell or that shell. That is how electron affinity varies on the periodic table across the period. Now, let's look at how EA can also vary once we're moving from the top to the bottom down the group.